would be, for instance, coin tossing. So in coin tossing, and this is one that kind of, is one that's kind of classic, because I think in coin tossing, if we have a single coin, we think about, for instance, heads and tails. And so technically, right, you flip a coin, you get one or the other. I think in our minds, what do we often do? We think of this really as being, for instance, 1 and 2 or 0 and 1, right? We mentally may say, well, why label them with heads and tails? In the case of a coin toss, it's easy to think, okay, this is trivial. I have a binary value, so I set it to something or something. But I think this points to the fact that there's this natural intuition we have, which is we want to take things that truly are heads, physically, heads, tails, and we want to assign them in some way that we can think about them mathematically. So formally, that's a random variable. Whatever this happens to be, if we want to take a function, we often do this implicitly, but if we want to take a function and basically say, I want to call this 1, I want to call this 2, then if you can imagine, I'm doing an experiment of flipping a coin, and I am looking at statements about heads and tails, I can use these numerical values to allow me to add them together. So for instance, as an example, imagine, I think we have heads, tails. Imagine in this case, we weren't just assigning 1 and 2, but we wanted to assign some reward to these. So imagine if omega equals h, so if the outcome happens to be heads, then x of omega equals 1, and then else this equals, then x of omega equals 4. This would be an example of a random variable used for, I'm going to say, well, it's 4 to 1. I want tails to be worth 4 points versus 1 point. I can now build, for instance, experiments in the 2100 sense. I can build experiments about probability of an event, like probability of getting so many points. I can build that experiment using this random variable. Later, not today, but in the next class, what you'll find is the nice thing is you'll do things like this. So you probably remember this. In 2100, it was normally the questions that were at the very end of the quizzes, the more complicated ones, which is you ended up with experiments that you had to do all the counting, you then had to do something with probability, and then you had to say something like, what's the expectation of this random variable? What's the expectation of this being above, what's the expectation of getting so many points? And this, you'll see this kind of notation on the subsequent class. But for now, the takeaway here is a random variable acts on the sample set, and it maps it to some numerical value that we can deal with. Okay, so we talked about probability. We talked about the fact that it's between 0 and 1 for any event. We talked about the fact that the probability of the entire set is 1. We talked about random variables over that. I think the last thing to mention, we talked about the fact that A being event. Just remember that this is a set, and therefore if I have A and B being events, we said that you need to remember that these operations are valid. So this is intersection. This is union. So again, refresh yourself on the fact that you'll take intersections and unions. And then we talk about this, for instance, for, let's give a concrete example. If we talk about the fact that we have a set of outcomes on a die, and we said, well, 2 possible events is that I roll an even, another event is that I roll an odd, so let's call the A's the evens, 2, 4, 6. And the odds, 1, 3, 5. That we can ask things like this: do these overlap? The intersection of these, this, right, the answer to this is null. There is no intersection. And again, now, if we think about what does this mean, it means that these two are not connected, no overlap. We use that term to mean, we use the term disjoint to refer to that. So again, this is a term you saw in 2100, which is anytime you have any sets, and in particular now we're dealing with these events, anytime you have a collection of events and you ask, when I take their intersections, do I end up with them, the intersections being null? These are disjoint. This will be an important property you'll use over and over throughout the class, which is asking yourself, is it really disjoint? So the reason, if you recall, the reason why this becomes important later when you're dealing with probabilities is if the events are not disjoint, you typically have to be very careful that you don't overcount. So remember in 2100, the place we would try to trip you up in terms of overcounting is we'd give you sets for which there was some small intersection, but it was non-trivial, and you would overcount because you would not take into account the fact that that event was counted in both sets. So for instance, let's see, we ended up with I think of an experiment on this one. We ended up with these two events, and we asked, for instance, about adding up to 6. Right? So it ends up that out of these two events, if we imagine that we defined these two events and we were rolling the die twice. So if we rolled the die twice, what we notice is, and we made some statement about, imagine that you roll the die twice. Imagine that both numbers come out of these two events. So meaning you get 2 things that are odd and 2 things that are even. And we made some statement about, could it add up to 6? You would need to be careful, for instance, to make sure that you appreciated that this set has a 2 and a 6, and that adds up to 6, as does this. And so you may, in your mind, think, oh, everything's disjoint. There's no way this can happen. However, like with the counting arguments you had in 2100, you have to think carefully about, are there intersections between the sets relative to the question you're asking? So again, we use this term disjoint to refer to intersections. These two sets are disjoint. If we then build, for instance, the sets of possible outcomes, so imagine we had prime and B prime. So imagine we said, now based upon, if you roll 2 things that are odd, if you roll 2 die, you get both values being odd. What's the sum of them? Then we now end up with a sum. You can answer that question, what's the sum of all the possible things? Well, I get, for the evens, for instance, it would be, I could get 2 plus 2 is 4. I could get 4 plus 4 is 8. I could get 6 plus 6 is 16, or 12. Sorry. I could get 2 plus 4, 2 plus 6, 4 plus 6. Let's see if I've gotten all of them. That twice, that twice, that twice, this and this, this and this, this and this, right? That's all. I don't think I missed any. Anyway, see, did I miss any of my counting? Similarly here, if I did B prime, I get 1 plus 1, 2, 6, 10, 4, 6, 8. Everybody with me? So experiment number 1 is just saying what if I roll one particular die, what's the evens and the odds? Now imagine a second experiment, which is I'm going to ask what happens if I roll a die twice, and I only look at those cases for which even or odd happen. Let's sum them up and look at the intersection between those. Now what I see is there is an intersection between these sets. So this set and this set are disjoint. So if I were asking about a single die and about even and odd, these are disjoint. If I now build an experiment, which is what happens if I roll die, and for the cases for which they're both odd or both even, and I sum them up, what happens to the sums, these sets aren't disjoint. So you have to be very clear what's the experiment you're running, what's the sets that you form, and then what's the query you do. That's the takeaway in terms of define your sets carefully, and based upon the experiment that you state, and then evaluate those sets. In 2100, we often enumerated them, but of course, what you're going to find is it's impractical. And what we're going to do is to enumerate them, so you have to think very carefully about how do you check for intersections. All right, so the next principle that you need to be reminded of, beyond disjointness, is conditional probability. So conditional probability is valid with respect to the following. Imagine you have two events, A and B. So again, assume that we have a sample space, assume we have a probability, assume we have two events that happen with respect to that. So that's the typical, in 2100, you have to state. So you recall we used this notation before in 2100. The probability that A happens given B. So remember, in English, we use the term given. We said that the way of interpreting this is the probability that an event happens given that I have knowledge that B has happened. And we said from 2100, this is defined as the probability of A intersect B over the probability of B. So the probability that an event happens, given that I know that B has happened, or if B were to have happened, it is equal to the intersection of these. So it's the probability of the intersection of these two events. I'm looking for those things in common between these over the probability of B. So this in particular will be huge in data science. This is a huge building block of a lot of the reasoning that will go on later in the course, and that is almost all of the methods that are used. Well, many of the methods that are used in data science are looking at these kinds of things. You're looking at probabilities that something happens given that you knew that something happens. And often what you're doing is you're trying to update these probabilities, meaning you're trying to update a probability concerning A given the knowledge that you have concerning B. Notice that all this builds upon what we just said over here. So you can't do the intersections and unions. You'd never be able to answer this. If you assume, so this is the definition in terms of conditional probabilities. It then leads us to another definition, which is independence. So we refer to two events, A and B, are independent. So this independent is a term we use, and they are independent if probability of B given A is equal to the probability of B, or equivalently, probability of A given B is equal to the probability of A, or probability of A intersect B is equal to the probability of A probability of B. I say or, meaning all these are mathematically equivalent. They all have effectively the following intuition. The probability of B happening, given that A happens, equaling the probability of B. So if we analyze that statement, what does it mean? It means knowledge of A doesn't help me at all. So if you view conditional probability as telling me that my probability of B is informed by the fact that I know something happened, the fact that two things are independent tells me, if I make the assertion that two events are independent, it's telling me that if I know something happens, for instance, A happens, it has no impact, no direct impact that I know of from a probability perspective that informs me as to what B will happen. Similarly, of course, if this is true, it means also that if I know A happens, if I'm asking about A, knowing about B doesn't happen. So the fact, conditional probability is effectively telling me when things are disconnected. Again, it goes back to this term, disjoint. It's telling me when these things are disconnected. This will become important later because you're often wanting to So the rationale for my statement of why conditional probability is important is that a lot of what we do in data science is trying to figure out when this is true, meaning when I can use information in B to help me predict A. Like, so from a data science perspective, I like conditional probabilities, meaning I like to be able to know something about B and use it to tell me something about A. Often in data science, worst cases, meaning challenging cases, are when I don't know anything, when the independence doesn't give me any hint about what's going to happen. And so I think in 2100, we often talk about independence as being great. In data science, we view it the other way, which is independence really is kind of worst case. Often what we want is to tease out or exploit interdependence and therefore use the conditional probabilities to my advantage. Okay? So if you're, like we would joke in 2100, if you happen to want to go to Vegas, you want to take advantage of this, right? Right? Your ability to tabulate conditional probabilities in your head becomes very useful because you're effectively saying, look, I've seen certain things, right? And we do this all the time. We've seen certain events happen, and the fact that I know those happen either increase or decrease or change the probability of the next event happening. Okay, so the next important point, again, this is all 2100 review, but the next important point that should come up is that term independence is with respect to events. We talk about two events being independent if the following are true. Similarly, we talk about two random variables. So two random variables, X and Y, we say these are independent if and only if for all possible make sure to use his notation, for all possible events A and B subsets of this, probability of A intersect B is equal to the probability of A. So, deciphering it mathematically, I think this is what we discussed in 2100. This is the one that I think is kind of easily logical, which is events are sets. When we get to random variables, we talk about these, since they're functions, right? We can't do X union Y. That makes no sense because these are functions. It would be like saying F and G. Like this intersection makes no sense. What it reminds you of, or what it should remind you of, is when we talked about functions in 2100, we often remind you that functions have a nice relationship with sets. So remember in 2100, we'd often say, function is a mapping from something, and you could really think of these as being tuples. Right? So F maps little a to little b, little c to little d. All this is saying is that if I colloquially use the term random variable x and random variable y being independent, behind all of that is you taking those functions, interpreting them in terms of their sets, and then going back and using this. So you will need to get familiar and comfortable with the idea that there's this interplay, just like you did in 2100, that when you talk about these functions, that they can be represented as sets, and then correspondingly you can go back and use all these definitions. But we don't often say these sets formed by these random variables are independent. We shorthand that and say these two random variables are independent. So I think it's just a matter of familiarity that you start to get comfortable with the idea of independent random variables. Random variables and the sets they generate. Yes?
What is sigma x and sigma y?
So using, let's see, in the notation, he's denoting, I want to make sure to be clear in his notation. He is assuming that if you have two outcome sets with probabilities, so we'll call it with respect to x, with respect to y, So imagine you have these two probability sets, two outcomes, two sample spaces. You can build random variables for these two, x and y. One possibility is that these are really the same, meaning omega x equals omega y. If that's the case, so imagine our coin flipping example. If we said, the original sample space is this, the random variables associated with this is x, and that happened to be, for instance, heads equals 1, tails equals 4, and imagine an experiment where I said, this is really the same, this is y, but now it's heads equals 2 and tails equals 16. This would be where these are the same, and you can talk about independence. You do all the machinery in terms of saying these are sets. Or technically the definition says these could be different sets, and you're looking, do those intersect? So for instance, imagine that experiment number 1, so this is one example, that's where the two sample spaces are the same, but our notation allows them to look different, need to be considered different. Or imagine the following, imagine I have a 6-sided die, and I have an 8-sided die. So I have two different die. Physically, they're different. The outcome spaces in terms of generating them are different. If I build a random variable based on this, though, for instance, x with respect to this and y with respect to this, I could ask questions about independence, because notice that there's an overlap between these. So therefore, it allows a possible overlap between events as I express them. Because for instance, if I said roll one die, roll another die, and I talk about likelihoods that they give you a 3. Notice that both of them, both die, even though they're physically different die, they could give you a 3. And that's the reason for this notation. He's trying to be as liberal, as open as possible. That when you talk about independence, you have to ask, what's my experiment? And even in this experiment, right, if I say roll 2 die, even though the die themselves are different, there is a similarity between them. They both have, for instance, a number 3, and therefore I'd have to ask questions about them. I could ask questions about them. Okay, so I think one more topic to hit, and then we're done for today, and that is, this was all discrete probability. The other one is continuous. Continuous. You similarly have now outcomes, but outcome is now not a discrete set. It is now a continuous set. And you have, let's see, in his notation, he just calls it f of x, which is the probability density function. I think in his notation, so that there's no confusion, in some textbooks you'll see, for instance, this set. I think in his notation he doesn't use this, but for those of you who are interested mathematically, this is all possible subsets of this set. For now, I think in his notation he kind of ignores this. He assumes that all of these are valid. So this is, for instance, often, for instance, the thing like the real line, and this is a function, for instance, over the real line. So unlike discrete probability, where you assign a number, probability to each one of the entities you get, in continuous probability, you now deal with the probability of events, where an event is a subset of this, and you now end up with, for instance, having to integrate over things inside of this with respect to, for instance, I'll use this notation, with respect to this. So previously, we had an outcome, we pulled out that outcome, we asked what's the number, 1/6. When we start dealing with continuous probability, we no longer, any particular outcome, if we pull out any particular outcome from this continuous set, the way of thinking of it, not mathematically rigorous, but it gives you the intuition. This is infinite, and it's not countably infinite. So if I pick any particular single outcome from this, the probability is 0. So I now have to kind of appreciate, the probability is 0. So really I'm in some sense talking about little pieces of the real line. I'm talking about little swaths of an event. So I'm asking things like, if the probability of the temperature is greater than something and less than something. So if my outcome set were valid temperatures in Salt Lake, if I ask about the probability that it's going to be 94 Fahrenheit, the probability in the continuous sense is 0. Right? And you can think about it. The likelihood of you landing right on that is 0. But if I said the probability that it was between 92 and 94, all of a sudden that has width on the real line. And that would be the probability of the event, and I'll just write it in shorthand. That would be that it's between 92 Fahrenheit and 94 Fahrenheit. And that's going to be an integral over what's the likelihood function. That's what this is, the probability density function of that temperature. Right? And I have no idea what it looks like in Salt Lake, but it's going to be the integral of some function that tells me how likely that is. That function could be uniform, could be flat, meaning it says that it's equally likely that it's anywhere between 92 and 94, or it could have different distributions. And that's part of what you'll see in this class, is that the shape of this is important. And we'll often kind of doodle it like this, and so we'll think of this as being, you've probably seen this, normal distribution. So it says that it lies somewhere between, that it has an exponential shape, and that the probability lies, the probability of something is the integral. For instance, if I said that it was normally distributed between 92 and 94, or had this shape between 92 and 94. So imagine all possible temperatures look like this. It's then you think about this is a tail. It's very unlikely that in Salt Lake it's going to be minus 100. It's very unlikely that it's going to be positive 200. It's going to be physically possible that it's 200 by probability 0. Right, the probability in Salt Lake probably looks like this. Well, for Salt Lake, it's probably that these are lighter. But this gives you some sense. This function gives you the distribution, the probability density function along that. So discrete side, we use sums and we use sets. The continuous side, we use sets, but we now move to integrals, and we hold on to this. So we call this the probability density function. And then the other one to be aware of is the cumulative density function. So this is what we just said here, the cumulative density function. For instance, f of t is equal to the integral from minus infinity to t of this d omega. So if we think about it now with respect to that diagram, what is this? This is effectively integrating under this curve up to whatever point I choose. So if I give you a probability density function for the temperatures, but then I ask you what's the probability that the temperature will be below, for instance, 93 point something, the probability will be the probability of the cumulative probability under this curve. So notice, for instance, if this curve integrates to 1, meaning the whole integral, the probability that the temperature is something, probability 1. The probability that the temperature is lower than 93. It's the integral of the probability distribution of this curve all the way here. And notice I've specifically drawn, notice if 93 was right at the peak, then you would expect the probability to be better than half. Does that make sense? So if I drew this distribution, the probability of 93 point something is the integral of all this, which is better than half, if you tabulate it. So these two are connected mathematically, and you should probably remember from calculus, you remember this formula from calculus, this of omega is equal to df d omega. So you probably remember the term antiderivative from calculus. Well, here, from a calculus perspective, that's where these two are connected. If you have a probability density function and you integrate it, you get the probability And then if you're trying to explain that mathematically in terms of calculus, you can explain it in terms of the integral. The cumulative density function or probability is equal to the integral of the probability density function. And then this is consistent with saying this. Or if I know the cumulative density function, I take its derivative, that tells me the probability density function. So in some contexts, you're given this, from which you can obtain this by integrating. In some cases, you obtain this, meaning you can reason about this, from which you can deduce this by taking the derivative of this. Okay. Any questions? So we have discrete, continuous. Discrete, we use sets, we use sums, we add up entities. Continuous, we still have sets, but they're now over the real line. We have a probability density function. If we evaluate it for any particular outcome, it's 0. If we integrate it over the entire domain, it's 1. Meaning the probability that something happens still has to be only 1. But now we have to deal with event sets that are more than a single entity. They have to be, you can think of it as some width. They have to have some, mathematically we call it measure, some thickness to them on the real line. And then there's an interplay between these two, probability density function and the continuous, or the cumulative density function, or the continuous probability that you get. All right, any questions? Okay, so that's it for today. I think this is the end of class, right? I'm probably slightly over. Pardon me? Okay, so that I'm on time. So I got an appointment, so I think I've got everything. I think I try to get it. I try to get it in 50 minutes. If there's any questions for me, feel free to see me right afterwards. Shannon will be back. He's traveling back on the weekend, so he will be here in class. Which hopefully I try to get that 6. I've got a 4 o'clock meeting with the DPR. All right, thank you.